Welcome to 3D vectors. This is going to be quite a long introduction. I've put in most of what I think is important to get to grips with the main idea of vectors. So if you need to take it in small chunks, feel free. Initially, we're going to look at the distance between 2 points in three-dimensional space. This should be just a recap in theory because you have covered it way back in GCSE. But it's useful to recall and understand why Pythagoras works in 3D as well as 2D. And then we're going to focus on what it means to work with vectors in 3D. You did some vectors in 2 dimensions, both at GCSE and in Year 12, but in 3D it can feel a bit different and a bit less intuitive. So I'm going to remind you of some of the key ideas, but we'll look at them all within the context of 3-dimensional vectors. We'll look at vectors between points, the magnitude, that is the size of a vector, what it means for two vectors to be equal, what it means for two vectors to be parallel, which is related but not quite the same, and then the idea of a unit vector, which means a vector with a length of 1, and how you can construct a unit vector pointing in the direction that you want. In a separate video, we'll look at how you calculate the angle between a vector and one of the coordinate axes. So let's start with the distance between points in 3D space. In order to understand why this works, we'll begin with a two-dimensional example. So you remember that we can apply Pythagoras. If we're looking at the distance from the origin to the point 3, 4, all we need to think of is the right-angled triangle that is effectively encoded within that picture. You move 3 along to the right and you move 4 up vertically. So to calculate the length, you use some Pythagoras. 3 squared at 4 squared, it's a 3, 4, 5 triangle. We can still work it out even when we're looking at points that don't involve the origin, and it's not too much nastier. You can still see, if you're looking carefully, the right-angled triangle in this question. It's effectively there. The base is there, and the height is somewhere up here. So you can see that all you need to calculate the length of this one is the difference between the x coordinates and the difference between the y coordinates. So from 1 minus 2 to negative 1, 4, we subtract y coordinate from x coordinate, y coordinate from y coordinate, x coordinate from x coordinate. And in many cases, this will give us a surd as our answer. If that's the case, leave it as a surd. Don't try to write down some approximate decimal version. We like the exact values. So what happens in 3D? Here's an image of the three-dimensional situation. The red axis pointing down and to the right is the x-axis. The green one pointing up and to the right is the y-axis. So you've got to imagine this as a sheet of squared paper that's laying flat on the desk. And then the blue axis pointing straight upwards is the z-axis. This now gives us a way of determining positions uniquely in 3D space. Interesting bit of trivia. Originally, when the coordinate system was constructed, the Cartesian coordinate system that we use by René Descartes, he was lying in bed watching a fly buzzing around a light, and he was wondering idly how he could describe the position of the fly uniquely in space. So when he first came up with the x, y, z coordinate system, it was three-dimensional. The two-dimensional version was just a simplified form of the original one. How far the fly was from his wall, how far the fly was from the floor, and how far the fly was from the window on the other wall. That gives you the 3 different coordinates that you need to uniquely determine any point in 3D. While I've been waffling, maybe you've been thinking about how you can calculate this distance, and I've shown you the right-angled triangle that we're going to use for it as well. So if we think about the point B, which is up at 3, 4, 12, we can calculate the distance from 0, 0, 0, the origin, to 3, 4, 12, by working out the distance from the origin to the point labelled A, which is the point 3, 4, and then the distance from A to B. So let's look at that on the diagram. A, the point 3, 4, we've already calculated a distance of 5 from the origin, and B, the point 3, 4, 12, is directly above the point 3, 4, 0, so it's a distance of 12 away from the point 3, 4, 0. And now you can see we're looking at a right-angled triangle. It's just vertical rather than lying flat on the desk. So Pythagoras still works just fine, and we'll square the 5, square the 12, add them together, square root, and we'll have the hypotenuse. You might also recognize this as a 5, 12, 13 Pythagorean triple. It looks a little messy written down, but I think it's worth writing it down in this fashion at least once, because we can now see the 5 that we constructed on the diagram. That came from doing Pythagoras with a 3, 4, 5 triangle. So we do 3 squared add 4 squared and square root it to get 5. And then we just square it to get 5 squared. So we might as well forget the square rooting and the squaring and call it 3 squared add 4 squared. And so we can put it into this formula, and it turns out just to be square all of the coordinates, or in the case of between 2 points, the difference between the x's, the difference between the y's, the difference between the z's, add together all of the squares, and then square root at the end. You might also be interested to hear that when Amazon determines which purchases you're likely to make, or when Netflix chooses your next favorite show that you ought to watch, they're essentially using this distance calculation. They don't have an X, Y, Z physical axis system, but they are tracking how likely you are to buy different products across hundreds or possibly thousands of different dimensions. They're looking at whether you've bought one thing or not, how many of this particular type of thing have you bought, and they're comparing you to other people by looking at the Euclidean distance, it's called. In other words, the distance using Pythagoras. They'll square the difference between one characteristic of you and that same characteristic of somebody else. And then they'll square the difference between a different characteristic you have and that same characteristic for somebody else, and so on and so forth. You can do it for as many characteristics as you like, and when you finish doing it, you add together all the squares, square root your answer, and it gives you a measure of how close your preferences are to someone else's. You can try this if you're bored during lockdown. You can write down a list of 5 things, maybe score the top 10 movies on Rotten Tomatoes, give them your own score from 1 to 5, and get a friend to give them a score from 1 to 5, and then look at the difference between your score and their score for all of the 10 movies, square them all, add them together, square root. That will give you a rough and ready measure of how close your preferences are to that of your friend. And if you try it with a bunch of people, you'll find there are some people that you get a very small score for. You're very close. And that's what this distance calculation will do for you. It doesn't have to be physical distance, it could be anything. Let's look at any 2 points. It's just the difference between the x coordinates, the difference between the y's, the difference between the z's. Square them, add all the things together, square root, and you've got your distance. Next, we'll try an example of this. Usually it's not as straightforward as here's 2 vectors, find the distance. It'll be framed in a way that allows you to use a bit of algebra. So we've got the coordinates of A. When they use the phrase respectively, remember, it means that you need to correspond the original A and B with the 2 coordinate values given to you. So A corresponds to 7 minus 1, 2. B corresponds to K, 0, 4. They've told you the distance, 3 units, and you're asked to find the possible values of K. So we set it up in the same way. We're looking for the distance. We need the difference between the x coordinates, the difference between the y's, and the difference between the z's. Square them all, add them together, square root. It looks a little messy, but it simplifies relatively nicely. And even though you've got a square root involved, that shouldn't bother us too much. In fact, you might have been tempted to get rid of it right at the beginning. If the distance is 3 units, the square of the distance is 9. You could say that straight away, and you'd immediately be left with a quadratic equation. As soon as you've got a quadratic, you rearrange so that it's in the usual format, and then you can either factorize or use the calculator to find your solutions. So we've got k equals 9 or k equals 5. Now, one of the reasons I picked this, apart from the fact that it shows you how to apply this with algebra, is that it might be worth thinking about why there are possible values, plural, for k. Why did we get 2 different numbers? We have a point in 3D space, we've got another point in 3D space that's a certain distance away. Well, if you think about it, there are lots of points in 3D space that are a certain distance away from a particular point. So the question, rather than being why is there more than one value of k, perhaps the question should be why are there only 2 values for k? And that comes down to the restrictions, the constraints that have been put on us. So we have a known y coordinate and a known z coordinate. There's only one direction in which this point is allowed to move, if you like. So if you hold out your finger in front of you, look at the tip of your finger, imagine that as a point in 3D space, and then imagine there is a wire running across the room near your finger. That wire effectively corresponds to all of the points that have only one direction they're allowed to move in. That's like changing the value of k. you're fixed in 2 different dimensions. There is only 1 dimension in which you're allowed to move. Maybe you've got something, maybe this example will make more sense. The 2 possible k values, let's imagine you've got a spider hanging above your head, some point in 3D space, and then you have a cobweb stretched tight across the room, and it passes by the spider. Here's our cobweb, stretch of cobweb thread. And then we're going to have another spider which walks along that thread, and what we're asking is, well, at which point is it exactly 3 units away from the original spider? And if you're looking carefully at that diagram, hopefully you can see that as that spider moves along, there are going to be not 1 but exactly 2 places where the distance matches any particular value. If it gets that close, it'll get that close twice, except in the special case where the distance happens to be the absolute minimum. You might also be able to see from this diagram why the very closest that a point can get to a line, you could calculate by recognizing that it will happen if you travel perpendicularly from the point to the line. If our little friendly spider you can still see on the screen wanted to get to that thread, its most efficient route would be directly down the middle of that isosceles triangle we've drawn, perpendicular to the thread itself. That will give it the shortest possible distance. And then either side of that, there are always going to be 2 different places that are a particular distance away from the spider, because the other spider gets closer and then it gets further away. If you want to investigate this a little better, there's a 3D version of a GeoGebra file. You can mess with the value of k and watch the actual points move around. Next, we'll look at what vectors look like in 3D space. Instead of just coordinates, we'll consider a vector. And there's a really important idea that you need to get clear in your head about vectors compared to points. The point 3, 4, 12 is a point with coordinates. It basically has a position, and that's all it is. There is a vector which might be associated with that point. You might call it the vector OA with an arrow over the top. And it's called a position vector because its job is also to define a position. But vectors are a bit more powerful than just coordinates. You see, generally speaking, a vector is considered to be a way of moving from one point to another. That's why when we write the vector OA with an arrow, we're suggesting that this vector is an instruction that will get you from O, the origin, the point 0, 0, 0, to the point A, the point with coordinates 3, 4, 12. So we'd write OA, and we write it slightly differently to coordinates. We usually put it in a vertical column. You'll sometimes see, particularly in the book, where they don't want to spread across multiple lines, they'll use IJK notation. So this would look like 3i plus 4j plus 12k. But we're not going to worry about that too much here. We'll focus on the columns because they're the most fundamental notation that you'll come across. So the vector OA represents an instruction that will move you from the point O to the point A. You can add vectors together, and this is a really important idea that you might remember from GCSE even. If you go from O to A following a vector instruction, and then you follow another vector instruction that takes you from A to B, the overall result is equivalent to the vector that takes you from O to B. So the journey doesn't matter in this context. It's the overall result that matters. It's like looking for the displacement rather than the distance covered. If we know the coordinates of B, we can find the vector that takes you from the point A to the point B. So OA is the position vector of the point A. OB will be the position vector which is associated with the point B. But AB is a vector that will take you from the point A to the point B. And by rearranging this little equation we've got up here, we can see how AB can be rewritten as OB minus OA. And in a sense, that should make sense to you. If I say to you, how do you get from 30 miles up the M1 to 37 miles up the M1? You'd do 37 minus 30, and you say, oh, you just have to go 7 miles up the M1. That's what's happening here. We've got the destination point's position relative to the original point's position, OB minus OA, where you want to get to minus where you've already got to. How do you save up £1 million? Well, it's pretty easy if you start with £950,000, because the gap is just the million minus the 950,000. So how you get from A to B is by considering where you want to get to, OB, relative to where you already are, OA. And here's what it looks like when you do the calculation. Each component effectively gets its own little calculation going on. So you could almost imagine there were lines separating these. 5 minus 3 is 2. 2 minus 4 is negative 2. And minus 10 minus 12 is negative 22. So each line gets the calculation applied to it. And overall, we get this 2, negative 2, negative 22. That's the instruction that you would need to follow if you were sitting at the point A and you wanted to move to the point B. And you can check that that makes sense. If you're at A with x coordinate 3 and you want to get to B with x coordinate 5, you're going to need to move 2 in the x direction. In the y direction, you need to change a 4 into a 2, so you're going to move negative 2 in the y direction. And in the z direction, you go from a high of 12 to a low of negative 10, so you need to move down 22. We're going to look a little bit more closely at that vector now, the vector that takes you from A to B. If you start at A and you move 2 in the x direction, negative 2 in the y direction, and negative 22 in the z direction, you will end up at B. But vectors are not constrained to a particular position on the coordinate axes. They can start from anywhere you like, and they will just follow the same instruction for moving. You could, for instance, start this one from the origin, and instead of taking you from A and leaving you at B, it'll take you from 0, 0, 0 and leave you at the point 2, minus 22. The vector itself just tells you what to do. It doesn't tell you where to start or where to finish. So if you change where you start, that will change where you finish. Here's another vector which should look similar to the other one. 1 minus 1 minus 11 is a perfectly scaled down version of 2 minus 22. It'll move you in the same direction as the vector AB, but it'll only take you half as far. So what we say is here, the direction of the vector is the same, but the magnitude or the size of the vector is halved. This vector is a scalar multiple of the vector AB. Scalar just means a number that doesn't have a direction, as opposed to a vector which has a direction and a magnitude, a size. Scalars only have a size. So we can multiply 2 minus 2 minus 22 by, say, a half, and that'll get you 1 minus 1 minus 11, a vector which is half the size. So if you start from A and follow this vector, you'll only get halfway from A to B. If instead you take your original vector and you multiply it by 4, it'll get you 4 times as far as it would have done previously, but in the same direction. You can also apply Pythagoras directly to a vector. So if you're asked to find the distance between a point A and a point B, and you've got coordinates, then you could do what we were talking about before. You could do the x-coordinate of A minus the x-coordinate of B, and then the y-coordinate of A minus the y-coordinate of B, the z-coordinate of A minus the z-coordinate of B. Square those things, add them together and square root. But that's equivalent to squaring each component of this vector, 2 squared, minus 2 squared, and minus 22 squared, and adding those together and square rooting the result. You should find you get 2 root 123. That's a relatively quick way to find the distance between 2 points, but it's also worth remembering when you find the magnitude of a vector, it's equivalent to the length of the line you would draw if you drew a line from the starting point to the ending point of that vector. All 3 of these vectors are going in the same direction, and that is the fundamental definition of parallel. Parallel means the direction is the same. So every single one of these vectors, if you drew them out, some of them will be longer than others, but they would all be pointing the same way. We are going to talk about equal vectors, what it means for 2 vectors to be identical, and then we're going to come back to that idea of parallel vectors and discuss what the requirements are, what you need and what you don't need to be a parallel vector. For 2 vectors to be equal, every single component in each one must match. Seems kind of obvious when you think about it, but it's worth stating and making it clear. The vector 3, 4, 5 is going to be the same as the vector 3, 4, 5, and only the vector 3, 4, 5. You can't change the 3 and the 4 around, you can't make it bigger and expect it to be the same. It might be going the same way, it might be parallel, but it's only going to be equal if every single component matches. In this case, for instance, we have what is effectively a single equation, but in reality, hidden within it are 3 different equations. In order for these 2 vectors to be equal, we need the x-coordinates to be equal. 1 must equal 1. That's okay, that's always true. We'll need the z coordinates to be equal. Minus 3 must equal k. Well, okay, we can make that work. We just need k to have the value negative 3. And then we need the y coordinates to be equal. And they're not. 2 is not equal to 1. That's never true. Therefore, these two vectors are never the same. Doesn't matter what value of k you give, the vector 1, 2, negative 3 will never be the same vector as the vector 1, 1k. It's worth mentioning vectors may have the same size and yet still not be equal. In fact, they could satisfy either of the two conditions, but unless they satisfy both, they're not equal. They might be going the same direction, but one is bigger than the other, or they might have the same size, but one is pointing a different direction to the other. So for instance, the vector 1, 2, 2, if you square its components, 1, 4, 4, add them together, 9, square root 3. We get the size of the vector 1, 2, 2, the magnitude is 3. But the magnitude of 0, 0, 3 is also 3. But clearly those vectors are not the same. They take you the same distance, but they take you in very different directions. So they are not equal. Let's try an example from the book on equal vectors. This is from exercise 12b, question 3. It tells us that a plus 2b is equal to 5i plus 4j, and it asks us to find the values of p, q, and r. So we know completely the vector a, 1, 2, negative 4, and we know nothing about the vector b until we're given this equation. Well, this is the equation we're working with, so that's what we're going to construct. It's worth noticing that on that second line, you could be forgiven for thinking that a and b were two-dimensional vectors, but in reality they're both three-dimensional vectors. So we have a plus 2b is equal to the vector 5i plus 4j. In reality, I'm writing that in column form, so I'm making it explicit. 5i plus 4j plus 0k. Then we're going to write out the values of a and b. A and b are both vectors, so I'm going to substitute those into my equation, and I'm going to simplify the left-hand side. I've done two lots of every single thing in the second term. That's where the 2p, the 2q, and the 2r come from down here. And then I've added the first bit. So 1, add 2 lots of p, 2, add 2 lots of q, and minus 4, add 2 lots of r. Now what's important here is that when you're looking at an equation in vector form, a 3D vector equation is effectively the same as 3 one-dimensional equations solved simultaneously. So we need all three of those equations to simultaneously be true. We need the top component to match. 1 add 2p must equal 5. We need the middle to match. 2 add 2q must equal 4. And we need the final term to match. Minus 4 add 2r must equal 0. Therefore, we get our values for p, q, and r, 2, 1, and 2. And those are the only values that work because they are the only solutions. Now let's look at parallel vectors. Remember, the idea behind parallel is same direction. These vectors need to be pointing in the same direction. This is how we determine from a vector written in column form whether it is parallel to another vector written in column form. We can check to see if one of the vectors is a scalar multiple of the other. For instance, 2, 3, 4 is parallel to 10, 15, 20, since 10, 15, 20 is just 5 times the size of 2, 3, 4. We could equally well put this the other way around and say that 2, 3, 4 is 0.2 times the size of 10, 15, 20. If one vector is parallel to another, then the other is parallel to the one. This is what the vectors would look like, roughly speaking. If you've got two vectors that are parallel, one of them may well be longer or shorter than the other, but they are going in the same direction. Here's another example, though, that seems to break that idea of going in the same direction. So we have to be a little more careful and precise with our wording. 3, negative 2, 1 is parallel, by our definition, to negative 6, 4, negative 2. And that's because we can show that one of them is a scalar multiple of the other. Now, the slight unease we should have here is related to the fact that these are most definitely not going in the same direction. So if you use that slightly vaguer definition of parallel, going the same way, we'd have to say these are not. But in the sense that two lines are parallel, in the sense that these two vectors, you could follow them forever and you would never cross the path of the other one, in that way they are parallel. And since that's the definition and the usage that we generally rely on for these vectors, because often we'll have a situation where you can move forwards or backwards within the direction of a vector. We treat these as parallel in exactly the same way that we treat the others as parallel. But we have a slight added detail we write in. We say the vectors are in the opposite sense. This is due to the negative scale factor that was required. If we want to change 3, minus 2, 1 into the vector minus 6, 4, negative 2, we need to multiply by a negative scale factor. And similarly, we'd have to multiply minus 6, 4, minus 2 by negative a half to turn it into 3, minus 2, 1. That shows that the vectors are pointing in exact opposite directions, but because they're exact opposite directions, the vectors are still parallel. Let's try an example involving parallel vectors now. We're told that we need to show that a particular vector is parallel to another vector. That vector is itself a combination of the two vectors they've given us, a and b. So the first thing I'm going to do is work out what 3a plus 2b would look like if we write it in its fully simplified form. We multiply each component in a by 3. We multiply each component in b by 2. We get this. Then we can add component by component. The I components, 9 add negative 6. The j components, 6 add negative 4. And the k components, negative 3 add 8. That gives us 325. All we need to demonstrate now is that 325 is parallel to 6, 4, 10. Hopefully you can see fairly easily that by doubling 325 you get 6, 4, 10. We can write this in a couple of ways. You can write 6, 4, 10 equals 2 lots of 325, or as I've done, 325 equals half of 6, 4, 10. They're scalar multiples of one another, therefore they are parallel. It's not always so obvious when you've got two vectors that are parallel that they are, but you can test for it pretty easily. If you divide the I component of one by the I component of the other, and you do the same for the j and the k, if they all match, then whatever you get when you divide them, that scale factor is the single scale factor you need. If they are all scaled up, they're in the same ratio effectively. So we've got the ratio 3 to 6, 2 to 4, and 5 to 10. They're all equivalent ratios. Your ratios might be messier, but if they're the same, if they're equivalent to one another, you're looking at parallel vectors. If the ratio is a negative, they're parallel, but they're in the opposite sense. And if that scale factor is positive, they're parallel in the same sense, because they're not only never going to cross no matter how far you go, but they're also moving in the same direction if the scale factor is positive. Here's a few true or false questions. It would be a good idea to pause the video at this point and see if you can answer these. If you think that the statement is true, see if you can give a nice clear explanation of why. It might involve diagrams. If you think it's false, try to find a counterexample to show why it's false. Feel free to stick with just two-dimensional vectors if it's easier to visualize. It'll certainly be easier to draw diagrams for 2D vectors. When you think you've got some answers, unpause and I'll go through them. So question 1, if two vectors are equal, they are parallel. Well, equality is what we call a stricter condition than parallelity. If two vectors are equal, every single component is the same. They have the same magnitude, they have the same direction. Every component is identical. So you could say that a vector that is equal to another vector is the same as the other vector in a very real sense. And the scale factor between the two would just be 1. There is a scale factor, the scale multiples of one another, therefore they're parallel. But the converse, if two vectors are parallel, they're equal, that one isn't true. Parallel vectors are only required to be a scaled up or down version of the original. And they could be the same, but they don't have to be. So 2, 3, for instance, is parallel to 20, 30, but 20, 30 is bigger, so they're not equal to each other. Question 3 seems to be correct. If u equals kv, in other words, if u and v are scalar multiples, and if the size of u equals the size of v, then they're equal. Well, surely we now have the same magnitude and the same direction, right? Well, almost. The same direction is not quite the same thing as saying two vectors are scalar multiples. If your vectors are parallel but in the opposite sense, then they're not equal, even if they happen to be the same size. So this is an example that breaks it, a counterexample. Minus 2, 3 is the same size as 2 minus 3, and it's parallel with it because there's a scale multiple. The scalar multiple is negative 1, but because the scalar multiple is negative, they're not going the same direction, so they can't be equal. If, on the other hand, you restrict k to be positive, then absolutely they are equal, and that would make it true. Question 4. This is something which is related to the triangle inequality. It's effectively a restatement of that. The triangle inequality is essentially the idea that if you walk around a triangle following two of the sides, compared to following just the one side that would shortcut those two sides, it'll take you longer to go around two sides than the shortcut, which seems pretty obvious. Well, in this case, we're saying, what if the size of two vectors added together is equal to the size of each separate vector added? In other words, the distance between your starting point and your ending point is the same as the length of your first journey and the length of your second journey added together. This is probably easier to visualize with pictures, but it's not necessarily true to say that the two vectors have to be the same for this to work. If they're going in different directions, it breaks, certainly, but provided the two vectors are parallel, we can still make this work. So you can see what's happening here. As long as the two vectors are going the same way, or going in exact opposite directions, opposite sense, then this result will work. It means you're essentially moving in the same track. So adding the two vectors will just give you another vector going in the same direction. Question 5, if u is a scalar multiple of v, then u plus v is a scalar multiple of v. This one is true. You can see it algebraically if you like, or you can think more visually. If you have two vectors which are parallel, and then you add them together, you generate another vector which is also parallel. They can't end up taking you in any different directions because both of them are pointing in the same direction, and any multiple of either of them, or any combination where you add or subtract them, will just give you more vectors in the same direction. Now let's finish off with unit vectors. Unit vector is an idea that hopefully will make sense now you know how to find the size of a vector and you understand what it means for a vector to be parallel to another vector. A unit vector essentially means a vector with a magnitude of 1 unit. So it has a length of 1. And there are some nice ways to visualize this. In 2 dimensions, you can think of the unit vectors as being any vector which takes you from the origin to the edge of the unit circle. So it could be the vector 1, 0, or the vector 0, minus 1, or it could be the vector 0.6, 0.8. Any vector that when you work out the length you get an answer of exactly 1 is a unit vector. And by thinking about this unit circle idea, you can see that there's an infinite number of them. For any direction you can think of, including all the ones that you can't, there is a unit vector that corresponds to that direction. All we've done with the idea of a unit vector is to scale down any vector we like, any vector you might ever have. You can scale it down so that the size is 1, but the direction is the same as it always was. In 3D, we've got an analogous idea, but you need to try to think of the unit sphere. So this picture may be a little difficult to make sense of what's happening, but with our red, green, blue, x, y, and z axes, we have a sphere which has equation x squared add y squared add z squared equals 1, by the way, because the distance from the origin is always 1. You can pick anywhere on that sphere and draw a line from the center to the surface, and that will be a unit vector in 3D with size 1. You can see there's an infinite number of these as well. In some sense, a wider range even than in 2 dimensions. You've got more flexibility. You could think of it in terms of on the planet Earth, if you were to construct a vector from the center of the Earth to the surface, and we treat the radius of the Earth as 1 unit, you could move to anywhere on the surface of the Earth, and there will be a unique vector that goes from the center to where you're standing. And that vector would always be the same length, it would always be 1 radius of the Earth, but the direction would change depending on where you choose to stand. And any vector in 3D can be scaled down so it has a length of 1, and then we would have a unit vector going the same way as the vector that we started with. So for instance, if we have the vector 1, 2, 2, we can turn this into a unit vector just by dividing it by a third. You can bring that third in. You can multiply it by a third and call it a third, 2/3, 2/3 if you like, so that you can see each individual component. It's 1/3 I plus 2/3 j plus 2/3 k, but it's often equally acceptable to write the scale factor just outside the vector, especially if it's a big messy surd. And we can see that it should be a third of it because the size of 1, 2, 2 is 3. If you use a bit of Pythagoras, you can see that the length of the vector 1, 2, 2 is 3. So we need a vector which is parallel to that one, going the same way, in the same sense, but it's 3 times smaller. So we divide by the size of the vector. Let's work through a question involving unit vectors, and you'll see how it works in practice. We're given the vector OA and the vector OB, and the first thing I'm going to do is write them out in column form, and they've asked us for the vector AB. Remember this key rule, AB is equal to OB minus OA. So to get from A to B, think about your destination, OB, relative to your starting point, OA. So where you want to be compared to where you're starting. OA, the vector 4, minus 1, minus 2 is the thing you're subtracting, and OB, the vector minus 2, 3, 1 is the thing you start with. And when you've got an answer, check that it makes sense. It's very easy to get this OB minus OA thing mixed around. But if you've got this vector, minus 6, 4, 3, then we can compare it to the position vector of A and see what happens if we follow it. If we start with 4i and then move negative 6 in the I direction, we'll get to negative 2, which is where we thought we should get. Similarly, to get from minus j all the way to positive 3j, we need to add 4j, and that's what we've got here. So it matches in the I direction, matches in the j direction, and we can also check the k direction. From minus 2k to k, you need to add 3k. For part B, they ask for the distance between A and B, but since we've already found the vector AB, the easiest way to do that is just to find the size of the vector AB. You'll notice again we've got this modulus sign coming up. When we do the modulus of a number, all we're really doing is ignoring the negative sign if there is one, essentially. But when we do the modulus of a vector, we're thinking more formally in terms of the size of the vector, how far away the end of the vector is from the start of the vector. But it's effectively the same as the modulus function that we've had before, just generalized to more dimensions. So we use some Pythagoras, we get an answer of root 61. And for part C, the unit vector, this relies on both parts A and B. Part A gave us the vector AB, part B gave us the length of that vector, and part C is asking for a vector that's going the same way as AB, but it needs to be smaller than AB. It needs to be exactly size 1. In order to shrink it down by the correct scale factor, I need to know how big it currently is. Turns out it's 7 and a bit long, so I need to divide it by 7 and a bit. I'm going to divide the entire vector by root 61. And that will give me 1 over root 61 times the vector. It may be a little confusing having this number written in a big bracket like this. You don't need to include the bracket necessarily, but remember the number in front is just a scalar, and the vector is what follows. If you were to expand this out, which you could, think of it like this. In other words, you bring the scalar into it. Minus 6 over root 61, 4 over root 61, 3 over root 61. That will be a perfectly valid form to leave your answer in. You could leave it in the form with the scalar in front as well if you chose. And for our final example, we're given 3 points, A, B, and C. We're asked to find the vectors AB, AC, and BC. So it might be worth here trying to imagine if we've got points A, B, and C, what we're working out. And when I do this, I pay very little attention to what the numbers are. It's not really important for this. I need to remember that my diagram is likely to be wildly inaccurate, not least because I'm drawing it in 2 dimensions when it should be 3. But we're asked to find the vector AB, that's the one that takes us from A to B, the vector AC, the one that takes us from A to C, and also the vector BC, which will take us from B to C. So essentially, I'm calculating all of these instructions to move from one corner to another of what looks like a triangle. So let's work those out. We do AB using the formula we've seen before, subtract OA from OB. We do AC in the same kind of way, get the destination, subtract from it the original starting point, and the same with BC. You can also check these by thinking about how you get from A to B. If you look at the vectors A and B, 8 needs to become 8, so no change. -7 needs to become -3, so you have to add 4, and 4 needs to become 3, so you need to subtract 1. So we can check that each of those makes sense. For part B, we're using Pythagoras to find the size of each of those vectors. Root 17, root 18, and root 25 is what I got. And then part C, they love these sorts of questions. And generally speaking, there is something useful and geometric that you can say as a result. I like the fact that this question doesn't, not because it makes it a particularly nice question, but so that you can see everything that you might look for instead of noticing something and not thinking about the rest. There are things that you might be able to say about a triangle. If I say to you, describe a triangle, you're probably going to be thinking in terms of, well, is it equilateral? Is it isosceles? Perhaps it's a right angle triangle. They're the main words that we might use to describe a triangle depending on its properties. We need to test for those things. So we're going to start by looking at whether it has any equal sides. If they're all equal, it's equilateral. If 2 of them are equal, it's isosceles. But remember, these are all different. We've got root 17, root 18, and root 25. So nothing doing there. It's definitely not isosceles, it's not equilateral. The other thing it might be, which is sort of unrelated to whether it's isosceles or equilateral in some sense, it's possible for it to be both isosceles and right-angled. We're looking for whether or not it's a right-angled triangle. The easiest way to do that is to see if the squares of the sides, the two shortest squares of the sides, add together to give the longest side squared. Well, we had root 17, root 18, and root 25, but the squares of those, 17, 18, and 25, don't combine in the way Pythagoras says they should. 17 add 18 is 35, not 25. So it's not a right-angle triangle. Since it's not a right-angle triangle, we can't say that. Since it's not isosceles or equilateral, we can't say that. Therefore, there's nothing interesting to say, but we still have a name for that. There's a name for the kind of triangle that is neither isosceles nor equilateral. It's called scaling. So that's all we can put for that one.